Hello, welcome to the third session of Polymers. The topic of discussion is glass. I am Srinidhi Kukila, and in this session we are going to discuss of these topics: introduction to glass, commercial types of glass, some of the engineering properties, that is mechanical properties, optical and thermal properties, different types of glass, and finally applications of glass. Glass is an immensely versatile material. It is used every day in numerous applications, many that most of us are not even aware of. We use it to drink beverages, to store food, and as windows in our homes and automobiles. But glass is also used in many unseen applications. For instance, glass components are used in medical diagnosis, electronics, building insulation, and as a reinforcement material in things like surfboards, wind turbines, orthopedic gas, etc. What is glass? Glass is a non-crystalline amorphous solid that is often transparent and has widespread practical, technological, and decorative uses in it, like window panes, tablewares, optoelectronics, etc. The most familiar and historically the oldest types of manufactured glass are silicate glass. Based on the chemical compound silica or quartz, the primary constituent is sand. The term glass is popular usage is often used to refer only to this type of material, which is familiar from the use as window glass and in glass bottles. Of the many silica based glasses that exist, ordinary glazing and container glass is formed from a specific type called soda lime glass, composed of approximately 75% of silicon dioxide, sodium oxide, sodium carbonate, calcium oxide are called lime, and several minor additives. Glass is an amorphous material that lacks a long-range periodic crystalline structure. Glasses can be formed through several methods, but the most common method involves heating raw materials into a molten liquid and then rapid cooling the liquid in such a way that atoms remain in random arranged atomic shape. Here in the image you can see the 2D representation of glass. The additional silica bond to oxygen is not visible, but in 3D representation it would be visible. Next, commercial glass type. The most common commercial glass types are soda lime silica glass, borosilicate glasses, and phosphate glasses. Soda lime silicate glasses contain components like silicon dioxide, sodium oxide, calcium oxide, etc. So they are having very low thermal shock resistance and an average chemical resistance. You open a refrigerator and take a look at the containers and jars within. Most likely they are made with soda lime silica glass. This family of glasses encompasses many of the glass compositions used to create food and beverage containers, decorative tablewares, and accessories, and of course windows. Soda lime silica glass compositions account for nearly 90% of the glass manufactured in the world, which is surprisingly very high. However, soda lime silica glasses are typically not as durable as other glasses. They tend to be prone to thermal shock failure and can degrade in chemical corrosive environments. Second one, borosilicate glasses. Borosilicate glasses, the primary components are oxides of silicon and oxides of boron. They are having high thermal shock resistance and very high chemical resistance as well. In harsh, demanding applications, they are commonly used for their superior durability. They can withstand thermal cycling with minimal effect. For instance, Pyrex, a commercial borosilicate composition created by Corning Incorporated, is commonly used for baking at home or performing experiments in lab. While many may quickly degrade in abrasive environments, borosilicate glasses have shown an ability to stand up to the task. They are commonly used in lighting applications where surface degradation and loss of transmitted light are undesirable. They are commonly commonly used for laboratory glassware, sight glass within industrial equipment, transformer bushings, explosion-proof lightings, and exterior aircraft lenses. Phosphate glass. They are mainly composed of the network form of oxides of phosphate. These glasses feature a high resistance to hydrofluoric acid, but otherwise they are relatively low resistance to the chemical coefficient. The compositions can be made more resistant to chemicals and environment by engineering the composition for the specific application. They are well suited for doping with various colorants, including transition metal ions and rare earth oxides. They are These colored glasses have found their niche in various medical, military, and scientific applications. Engineering properties of glass. Transparency of glass is the main property which allows the vision of outside world through it. The transparency of glass can be from both the sides or from one side only. Strength of glass depends on modulus of rupture value. In general, glass is a brittle material, but by adding mixtures and laminates, we can make it more strong. Workability of glass means a glass can be molded into any shape or it can be blown during melting. So it is a superior property of glass. Transmittance, the visible fraction of light that passing through glass is the property of visible transmittance. U value of glass represents the amount of heat transferred to glass. If a glass is said to be insulated unit, then it should have lower value. Recycle properties of glass. Any glass can be 100% recyclable. It can also be used as raw material in construction industry. Mechanical properties. Stress, strain and elastic property. You may be surprised to learn that glass is an elastic material on the atomic level, which is very astonishing. This means that under stress, glass will deform due to the nature of its atomic bonding structure. However, this change is not permanent, and when the stress is removed, the glass reverts to its original form. The stress on a glass is defined by force applied to a unit area. Applied stress can be homogeneous. The strain describes the deformation of glass. The elastic nature of glass is described by its elastic moduli. So this moduli tells you a lot about how much a glass will deform under stress and in what direction it will deform. Three important and commonly used elastic moduli are Young's modulus, Poisson's ratio, and shear modulus. It is very important to understand that while glass is elastic in nature on a microscopic level, it is also a very stiff material on the macroscopic scale. This means that for typical stresses applied to glass, the resulting strain is very small. But knowledge of Young's modulus can be very useful in predicting the strength or impact resistance of glass piece. Say you are designing a lens that needs to withstand large pressure without breaking, such as an exterior of submarine light. Strength. The strength of a material is the amount of stress that can withstand before fracturing. For a glass, for a glass which theoretically has small flaws are always present in real glass structure. Accounting to these imperfections, the strength of glass is proportional to the energy of the fractured surface, Young's modulus of the glass, and the size of the flaw. That is, the formula is 1 by 2 into gamma f into y by c to the power 0.5. When selecting glass as a material for your application, knowing the strength of the glass will help ensure it can withstand applied stress and meet specific requirements. Glassware used in naval applications such as navigation, warning, or signal lights must pass hydrostatic pressure tests according to some military standard. The glass lenses installed in exterior submarine lighting are required to withstand pressures of about 10 to 15 megapascals. Glasses most commonly fail from flaws at the surface when tensile stresses are applied. To test the strength of glass, standard test methods for strength of glass by flexure is often used. Hardness. Hardness is the ability of a material to resist being scratched, fractured, or permanently deformed by the sharp edges of another material. In other words, it is a measure of material's resistance to abrasion. You can measure the hardness of the glass by using indentation tests like Brinell hardness, Vickers hardness, Rockwell hardness, and some of the scratch tests like Mohs scale. Glass lenses that are installed in outdoor environments, such as exterior aircraft lighting, are often subjected to abrasive conditions. When designing a lens for such a harsh environment, it is important to know how the surface of your material will wear, since abrasion can adversely affect performance. When designing for an application that requires high strength, high transmission, and abrasion resistance in the face of extreme conditions, it is best to choose a hard glass. Impact resistance. Glass is often required to withstand not only continuous stress or surface abrasion but also impact. Impact is defined as large force that is applied instantaneously to one spot on the material. Glasses are said to be resistant to impact. if they retain their surface quality and also resist fracture. Impact resistance is improved with high values of strength, hardness, and toughness. The impact requirements of a glass part depend strongly on its application. A glass fit for one application may fail in another. Pebbles and gravel are often kicked up in the airfield runway by an airplane's wheels. Runway lighting systems must be able to withstand these impacts without failure. In contrast, in-ground pavement lights are subjected to different environmental impacts and as a result have different impact requirements. Chemical resistance. The chemical resistance of glass is a measure of its durability when it is exposed to or immersed in applicable chemicals. It is important to understand how glasses react to acids and bases, but it is important to know whether they degrade in water or even due to humidity in the air. Most commercial glasses, including silica, soda lime silicates, borosilicates, which is having high chemical durability. This is due to these glasses having strong bonds between atoms and high network connectivity. Before you can select a material for an application, you need to know what environmental conditions it will be exposed to. For example, exterior aircraft lenses can be exposed to a variety of harsh chemicals such as de-icing fluids, petroleum-based fuels, hydraulic fluids, and also air pollutants. Materials chosen for these lenses must be highly resistant to these chemicals in order to prevent degradation and failure. In some other applications, the lens or filter material may be required to withstand certain environmental conditions such as resistance to humidity. Glasses used in night vision imaging system applications need to meet humidity tests. The surface degradation of a glass is tracked as a function of time and relative humidity at a constant temperature. These are some of the mechanical properties of glass. Next is optical properties. Optical property of a material determine how it will interact with light. Most engineers use advanced software tools to simulate the properties of material and their impact on optical performance. With a few fundamental optical properties will help engineers pick the right material for their application. So some of the optical properties are refractive index, transmission, absorption, and wavelength dependency. Refractive index: light that is incident on a glass surface. As you can see in the image, it will be reflected at an angle equal to the angle of incidence and transmitted through the material according to Snell's law. From normal incidence, approximately 4% of light is reflected. This value is determined by the refractive index of glass. When a beam of light hits a glass surface, part of the beam is reflected and part is transmitted. The index of refraction of the glass determines not only how much light is reflected and transmitted, but also its refracted angle in the glass. So this angle of transmission can be calculated using Snell's law. When designing a lens that transmits light, it is necessary to consider the material's refractive index. Even a small change in the refractive index can affect the distribution of transmitted light. This can be seen where light travels through two identical shape plano-convex lenses with different in refractive indexes. Absorption. When light travels through a glass, the intensity of light is typically reduced. This absorption happens when energy of photon of light matches the energy needed to excite an electron within the glass to its higher energy state, and the photon is absorbed by the glass. The absorbance of glass is a function of wavelength, is often used to describe the decrease in intensity of light as it travels through glass. This value depends on the composition and thickness of glass as well as the wavelength of incident light. Rare earth fibers, earth glass filters are often used to calibrate the absorption and transmission of spectrophotometers. These glasses absorb light at a very specific wavelengths, which enable the calibration of well characterized absorption peaks across ultraviolets, visible, and infrared spectrums. Next, we will move on to the thermal properties of glass. It is critical to have a thorough understanding of glass thermal properties when designing with a glass lens or filter. When exposed to sudden or even gradual changes in temperature, improperly designed glass lenses will perform poorly and can even fail. Some of the thermal properties are coefficient of linear thermal expansion. Coefficient of thermal expansion is a measure of how much volume changes as a material is heated or cooled. For isotropic amorphous materials such as glass that have small thermal expansion, the linear coefficient is accurately described by one-third of coefficient of thermal expansion. So coefficient of thermal expansion is proportional to the volume and the temperature. If a temperature is unevenly applied to a glass, different areas of glass will expand by varying amounts and internal stresses will develop. So this could result in glass fracture or failure. Thermal shock resistance. Thermal shock resistance of a glass indicates how likely it is to break when its temperature suddenly changes. It is defined as maximum change in temperature that a glass can withstand upon rapid heating and cooling. It is related to internal stress necessary to cause cracking or failure, Poisson's ratio, Young's modulus, and coefficient of linear thermal expansion of the glass. It is often tested by taking heated glass lenses and rapidly cooling them through methods such as immersion in an ice bath. This type of testing can indicate the ability for glass lenses to withstand large changes in temperature when installed in applications. Glass lenses used with high power lighting, they can be exposed to lot of temperature changes, experience rapid cooling when exposed to rain, snow, or other environmental factors also. Next is thermal conductivity. It represents how well a glass conducts or transfers heat. So it is proportional to heat flow measured, cross-sectional area, and temperature gradient applied to the glass. Good thermal conductors will allow heat to travel through the material very quickly. It is often desirable for glasses to have low thermal conductivity in applications and act as thermal insulators. For instance, LED perform better in cooler temperature and will output more light. Specific heat. It is the heat needed to raise the temperature of the glass by 1 degree Celsius per unit weight. It is proportional to heat, mass, and temperature. The specific heat of a glass could be an important consideration for applications where glass operates at high temperature. Considering a lighting fixture that uses a glass lens with quartz halogen bulb, these bulbs often operate at high temperatures, outputting a large amount of heat. If the lens is designed with low specific heat, it will reach its equilibrium temperature faster and reduce the warm up time of the system. Glass temperatures. Some typical 5 important glass temperature are often discussed in production and designing the glass. That is melting point, working point, softening diatometric point, annealing point, strain point. Melting point is the temperature at which the raw materials melt at a liquid state. Working point is the temperature at which the glass melt in shaped or molded. Softening diatometric point is the temperature at which the glass begins to deform during heating when measured in diatometer. Annealing point is the temperature at which the residual stresses in a glass are reduced over a matter of minutes. Strain point is the temperature at which the residual stresses in glass are reduced over a matter of hours. Thermal dependence. Thermal dependence of other glass properties. Many glass properties may be affected by change in temperature. The chromaticity or color of a glass is often dependent on the thermal history. Red and yellow colors in glass are usually developed during manufacturing by a process called striking, where the glass is heated and cooled to promote specific color through oxidation, reduction, and precipitation reaction of the colorant. Glasses that are heated expand by an amount proportion to their coefficient of thermal expansion. This change in volume may also affect both the density and refractive index of glass. Next, we'll discuss the different types of glass. First one, float glass. It is made of sodium silicate and calcium silicate. So it is also called as soda lime glass. It is clear, flat, and it causes glare. They have a weight range of 6 to 36 kg per meter square. They are used as shop fronts and in public places. Next is shatterproof glass. They are used for windows, skylights, floors, etc. Some type of plastic polyvinyl butyral is added in its making process, so it cannot form sharp edged pieces when it breaks. Laminated glass. It is the combination of layers of normal glass. So it has more weight than normal glass. It has more thickness. It is ultraviolet proof and soundproof. They're used in aquariums, bridges, and many more. Extra clean glass. They have two special properties: photocatalytic properties and photophilic properties. Because of these, it acts as stain proof and gives beautiful appearance. Chromatic glass. They are used in intensive care units in hospitals, meeting rooms, etc. It can control the transparent efficiency of the glass and protects the interior from daylight. They may be photochromatic when light which has light sensitive lamination, thermochromatic which has heat sensitive lamination, and electrochromatic which has electric lamination. Tinted glass. It is nothing but colored glass. A color producing ingredient is mixed to the normal glass mix to produce a colored glass, which does not affect the other properties of glass. For example, coloring ions like iron oxide, sulfur, manganese dioxide, cobalt, chromium, titanium, uranium are used as coloring agent, which gives out different colors like green, blue, black, yellow, etc., and variations of these colors. Next, toughen the glass. It is strong glass which has low visibility. It is available in all thicknesses, and when it is broken, it forms small granular chunks which are dangerous. It is also called as tempered glass. This type of glass is used for fire resistance door, mobile screens, etc. Glass blocks. They are also called as glass bricks, which are manufactured from two different halves, and they are pressed and annealed together while melting process of glass. They are used as architectural purposes in the construction of walls, skylights, appearances. They also improve the aesthetic appearance when light passes through it. Next, glass wool. It is made of fibers of glass and acts as good insulating fillers. They are also fire resistant. Lastly, insulated glazed units. Insulated glazed glass units contain a glass which is separated into two or three layers of air or vacuum. They cannot allow heat through it because of air between the layers and acts as good insulators. They are also called as double glazed units. Applications of glass. Some of the applications of glass in aircraft is aircraft windows. They are made from a form of plexiglass such as Lexan polycarbonate or acrylic plastics. The outer plane of the aircraft window is about 12 thick. The inner plane is 4 thick. They are separated by 6 thick of air chamber, making a total thickness of 22 millimeters of entire window, aircraft window, which may seem thin, but the outer pane is thicker than the plane's fuselage. This material, aircraft window glass material, is lightweight, relatively strong, and you can see clearly through it. The glass is layered, and the middle layer usually has a tiny hole in it to get rid of condensation. So this concludes the third session of polymers. So the things we have discussed in the third session of polymers is what is glass, then most commonly commercial glasses used, like soda lime silicate glasses, borosilicate glasses, and phosphate glasses. Then some of the engineering properties like transparency, strength, workability, transmittance, U value, and recycle properties. Some of the mechanical properties and its applications, and then uh, some of the chemical properties, and then optical properties of the glass like refractive index, absorption, transmittance, and then thermal properties of glass like coefficient of linear thermal expansion, thermal shock resistance, thermal conductivity, specific heat, etc. And then we have discussed about the different types of glass and its application, and then applications of glass. If you have any doubts, clarifications, suggestions, please comment below. Thank you.